Alrighty, welcome back, mathematicians. We're going to continue on section 1.2, and that's all about combining functions and then shifting and scaling their graphs. So notice that we talked about functions last section 1.1, that they are all real numbers, right? I can add, subtract, divide, and multiply real numbers. So since a function's output is a real number, oops, that's not grammatically correct. It's implied that we can add, subtract, divide, and multiply functions together. We'll do MULT for multiply. So what does that look like? So if I have f plus g of x, that's how we can write that. We can also define that as f of x plus g of x. F minus g of x, it's going to look pretty similar. It's going to be f of x minus g of x. What about f times g of x? It's going to be f of x times g of x. Now remember that we can't divide by 0. So if g of x does not equal 0, we can say that f divided by g of x equals f of x divided by g of x. Alrighty? Now, we talked a lot about domain and range last section. So what is the change to the domain here? To the domain. Well, let's call the domain of f d of f and the domain of g d of g. Our new domain for f plus g of x, f minus g of x, and f times g of x is going to be the domain of f intersected with the domain of g. Intersection. So what that means is I need to be in the domain of f and in the domain of g. So usually intersections, we can also say, we say like domain of F and domain in G. Unions, flip that cup to a U, would be union. Those are usually denoted or. I'm in F or I'm in G. These, I need to be in both of them. So remember that case where G of X can't equal 0? So the domain of F divided by G of X is still the domain of F intersected with the domain of G, also intersected with, we'll call it, when X such that G of X does not equal 0. So I need that not to be in here. So this part excludes when G of X equals 0. We'll run through an example because that's a lot of math lingo that's kind of confusing. So our example is going to be when f of x equals what? What did I choose? Square root of x, and g of x is equal to 1 minus x. First, let's find d of f and d of g. So last lecture, I know that the square root of x, its domain, is going to start at 0. If I can draw a bracket correctly, there we go. No, what? What is that? Oh my god. 0 to infinity, and d of g is going to be so it's 1 minus x. So the biggest x can be is going to be 1, because anything greater than 1 is going to give me a negative under this radical, which is not okay. So I can put in negative 100, 1 minus negative 100, it's going to give me a positive number. So I can go down to any negative number I want. So I have from 0 to infinity, negative infinity to 1. So what does d of f intersection with d of g look like? Let's look at a number line. We'll call, where's like the center? Right here? Sure. 0. Let's call, oh, voice crack. 1, and this one, -1. So d of g is going to go from, let's make it a little thicker, 1 to all the way down here to negative infinity and on. Well, f of g, what's another fun color? It's a color that goes, ooh, orange. F goes from 0 to 1. So I kind of just got rid of the green. But you can kind of see that it overlaps at this one point. I think I had it right here. Yeah, beautiful, cool. So right here, that's our intersection. I'm including 1 and I'm including 0. So the domain of, that's too thick. Domain of f intersection with domain of g is going to be this closed interval from 0 to 1. Alrighty. So what if we, so this is going to be the domain for f plus g, f minus g, and f times g But what about the domain for f divided by g of x? Well, let's see what that function looks like. So f divided by g of x is f of x divided by g of x, which equals, that function's in my way, what is f of x? It is the square root of x divided by square root of x divided by square root of 1 minus x. I can rewrite that as the square root of the whole thing, x divided by 1 minus x. Well, now I know it's when this bottom part can't be 0. Cannot equal 0. Well, that doesn't equal 0 when x is 1. So now I'm going to have 0, 1 with a soft bracket because I cannot include x equals 1. That's also a good example of how different a closed bracket versus I call these a hard bracket and these a soft bracket. Brick wall says I need to stop right at 1. A cloud says I can kind of approach 1. Alrighty? So that's adding, subtracting, multiplying, and dividing. And we'll work on a few more examples in a little bit. So what if we put a function inside of another function? We define this as what is called composite function. So if f and g are functions, the composite function, so composite is a word that we want to keep track of. We can say f, and then it says open circle g. We say f composed with g is defined as follows. F of g, f composed with g of x, we say f of g of x. So now g's output is f's input. Alrighty, so question of the day. Does f of g of x equal g of f of x? Not always. It's actually more a case that they don't. So let's look at f of x equals to square root of x. Really love that function. And g of x equal to, let's just do x plus 1. Alrighty, so if I'm doing f of g of x, I'm going to have f of, g of x. So that's going to look like the square root of g of x Well, g of x is x plus 1, so this is going to be the square root of x plus 1. Well, oopsies. Ah, my gosh, technology is so hard. Okay. Well, g of f of x, g composed with f, so g of x takes my input and adds 1. So I'm going to have f of x plus 1. So that's going to give me the square root of x plus 1. Oh my gosh, I brought my 1 up here. All right. So if I'm looking at these two functions, they're very different. And we'll actually get to how I know what they actually look like in a little bit. But let's just finish talking about the domain of f of g versus the domain of g of f. So domain of f of g, right, we're looking right here, x plus 1. So if I plug in, that's going to equal, the smallest number in here is going to be 0. So when x plus 1 equals 0, x is going to equal -1, and then I can add any other positive number. Right, because x plus 1 equals 0, x equals -1. Well, this one, the domain is actually pretty similar to what I've already seen. Right, that plus 1 doesn't change my domain at all. So I'm just kind of looking at square root of x, which I know is going to be including 0 all the way up to infinity. Alrighty? So, turning a page of my notes. Let's talk about shifts. We can kind of see in this example that we used earlier, I'm adding 1 right here, right in next to x before this radical can touch it. And then right here, I add a 1 after letting the radical touch x. So shifts. We say that vertical shifts take this form. So vertical if I have f of x equal to, oh no, excuse me. Boop. Y equal to f of x plus k. K is just a real number here. If k is greater than 0, so a positive number, no, k equaling 0 here would be kind of silly because then I wouldn't shift at all. So if k is positive, we're going to shift the graph up k units. Ooh, let's use some highlighters. Can I change the color? What? Hell yeah. Shifting up. It gives me some like blue vibes. Wow. So yeah, we're gonna shift up k units. If k is less than 0, we're going to shift the graph down. How many units? The absolute value of k units, right? K is -2. I want to shift down 2 units. Down kind of gives me like green vibes, like Mother Earth. All right, cool. So those are vertical shifts. Horizontal shifts we write that as y equals f of x plus h. Okay? So horizontal shifts work opposite of what you think they're going to do. Think of it as h is grounded. It's in the house, this house being these parentheses, because it's doing the opposite of what you think it is, so it's grounded. Okay? So a horizontal shift, so let's say if h is greater than 0, we're going to shift, come on, the graph. It's a positive number, you want to shift right, but it actually shifts left h units. If h is less than 0, shift the graph right. Absolute value h units. Okay, so let's highlight these. Left, right gives me pink vibes. Left, ooh. Feeling orangey with it. Is that too close? Whoa, way too close. Okay, right. Left will do yellow. Okay, cool. Wow, so pretty. Okay. So, left and right. So we all know f of x equals x squared, right? We've seen that graph. We know that graph. What about if g of x equaled x squared plus 2? H of x equaled x plus 2 squared. You see how I added a shift, one vertical, one horizontal. So we're gonna actually do this all on one big graph. There's probably a way to make graphs on here, but you know what? YOLO. Alrighty, so x squared, each block's gonna be 1. So we're gonna x squared 1, 2, 1, 2, 3, 4. Okay, oh my god. Okay, beautiful. So that's what we're gonna call f of x. So I have x squared plus 2. So that looks something like this. Don't you agree? And k is positive, so we're going to actually move up 2 units. So now g of x, I'll make it a light blue. I'm going to go up 1, 2 units. Sure. Alrighty, so that's g of x. And then h of x has a plus 2. That looks like a horizontal shift. And since 2 is a positive number, we are going to move to the left 2 units. So h, let's call it, oh, does this yellow like look good? Oh god, absolutely not. Okay, cool. And we're gonna move it to the left 2 units. So now we're over here. Oh my God, what is wrong with my graphing abilities? Something like that. So H moved over 2 units to the left, while G moved up 2 units. Let me check that I did everything right and not completely wrong. Okay, good. Now, that's just moving around or shifting. What about scaling? If I want to shrink this graph or stretch this graph, what is that going to kind of do? So we call that scaling. Did I underline this? Okay, good. So we had vertical and horizontal with shifts up and down. Scaling, still vertical and horizontal, but now we have stretch and compress. So we say, why? What is that figure? Get out of here. I do not like you. Okay. So y equal to some c times f of x. Oh yeah, c is a real number, and c is actually greater than 1. Because this would be kind of confusing if it wasn't. So c is greater than 1. So this is going to stretch f vertically by a factor of c. Obviously, if c equaled 1, the graph wouldn't move at all, it wouldn't stretch, but I'm going to stretch it vertically. Vertically has 2 L's, don't come for me. Y equal 1 divided by c times f of x. Opposite of stretch is compress. F vertically by a factor of c. Now we had things on the outside of f of x. Now what if it was inside the f of x? So y equal to f of c times x. We're going to, remember, if it's on the inside, it's going to do the opposite of what we think. So it's not going to stretch now, it's going to compress. And since it's on the inside, it's going to compress f horizontally. Oh, God, 2 L's maybe, okay. By a factor of c. If y equals f of x divided by c, it's going to stretch f horizontally. By a factor of c. All right, so let's look at what that kind of means. So hold on, I don't want that there. Erase. So what if we looked at the square root of x, right? We love that one. That is what we're going to call a rough estimate of what that graph looks like. Now I want to stretch it by a factor of 3. So I'm going to stretch it up stretch, 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 stretch. And that's how we get 3 times square root of x. And if I want to compress, by 3, well, I am compressing vertically by 3, so I'm going to have square root of x divided by 3. Also the same as 1/3 times the square root of x. So that's stretching and compressing vertically. What about horizontally? So same graph, sort of. And I now want to stretch it horizontally. So stretch. And that's going to be the square root of x divided by 3. And if I'm compressing, I'm kind of getting my own way. Well, it kind of looks like they're a little bit of the same. They're not. I'm going to show you why. Square root of 3x can be written as the square root of 3 times the square root of x. So I'm compressing by a factor of 3 horizontally, but I'm I'm scaling vertically by a factor of square root of 3. So even though it kind of looks like, oh, if I stretch horizontally, that's the same as compressing vertically, graphically, you might look the same, but by what factor you're stretching changes depending on each function. So that's why they're not equivalent. All right. So now we have a special case of scaling of what if c equals -1, right? Earlier we said that c is greater than 1. Having it less than 1, kind of stretching and compressing, like if I have like 0.5, that's the same as 1/2. That's why we keep it greater than 1. But what about -1? This is actually called reflection. So if, I want to underline this. So if y equals negative f of x, that's going to reflect f across, that is not how you spell that word at all. Wow. Across the x-axis. Y equal to f of negative x, we're going to reflect f across the y-axis. So a little example of that, we're going to choose our right-hand man, square root of x. So we're going to do full picture here. So square root of x right here. What about square root of negative x? Well, I can't have a negative number. Like I'm now putting a negative. I'm going to reflect over the y-axis. This is y. Oh, come on. Y. This is the x-axis. So if I reflect over the y-axis, that's now going to be square root of negative x. And negative square root of x is going to reflect over the x-axis. All right. So I'm reflecting over, if the negative's on the outside, I'm going to be down here reflecting this way. If it's a negative on the inside, I'm going to flip that way. Alrighty. So now let's put everything that we've used together. I can tell you the recipe for an equation, and you can tell me the end process. So what that means is if we're given that f of x equals x to the fourth minus 4x cubed plus 10x, I can tell you to move, reflect, stretch one way, and you can give me a whole new equation. So if I say compress horizontally by a factor of 2, whoa, followed by a reflection across the y-axis. So compress horizontally. Let's scroll up in our notes to check that really fast. I want to compress horizontally. Boom, boom, right here. So I'm gonna have something that looks like that. F times c of x. Well, we were told that we're going to have a factor of 2. So I'm going to first find what f of 2x is, because that's going to compress horizontally. So if I want to highlight that, it's pretty purple, by a factor of 2, that's what this is. So I'm going to plug in everywhere there's an x here, I'm going to plug in a 2x. So 2x to the fourth minus 4, 2x to the third plus 10. That's going to equal 2 to the fourth is 16, x to the fourth minus 2 cubed is 8, 4 times 8 is 32. Yeah, 32. X cubed plus 10. Now I want to reflect it across the y-axis. So reflect across the y-axis, I'm going to affect x again. So now I'm going to have f of negative 2x. I already found out what 2x is. Actually, let's call this g of x f of 2x. And now I have g of negative x. So that's going to equal 16 negative x to the fourth minus 32 negative x cubed plus 10. Well, that's not going to change anything because of that 4, but this will make a positive out of negative 32. So I'll have 16 x to the fourth plus 32 x cubed plus 10. I also could have kind of just bit the bullet and done f of negative 2x. I also would have gotten the same thing. So those quotes mean. Okay. So now what if I ask you to compress vertically by a factor of 2. And reflect. I need to learn how to spell the word across. Across the x-axis. Really want to fit that one in. Okay. Well, let's do it all in one sweep like we could have done earlier. So I'm compressing vertically. Let's go back and check my notes. Compressing vertically. That's on the outside. So I'm going to divide by 2. And I want to reflect across the x-axis. That's also on the outside. So that means that f of x is going to go from, we're going to be f of x, and then I'm going to multiply -1/2 f of x to get this transformation. What's that going to look like? Let's see. So I start off with x to the 4th minus 4x cubed plus 10. And I'm going to divide that all by 2. And also a negative. So that'll give me negative x to the 4th divided by 2 plus negative times a negative, 2x cubed, 4 divided by 2 is 2, minus 10 divided by 2 is 5, right? And that is my new equation. So now we can see a fun little example of how it's different to compress vertically, which is where I got this 1/2 from. And reflect across the x-axis, which is where that negative came from. Alrighty, so that's going to wrap up 1.2. And then all we have the rest to do today is 1.3. Woo! See you guys in a little bit.